Alright, so what is root locus? Alright, so root locus is a graphical method for examining how the roots of a system change with variations of a certain parameter, commonly the gain of the uh, feedback systems. So you take note of this. So what we want to do for the root locus is to examining how the roots of a system change with variation of certain parameters, commonly the gain of a feedback system. So what we are interested is actually in the root locus is we have the gain, and then when we change the gain from 0, 1, 2, 3, and so on and so forth, we can see that the roots of the system, the closed loop system, will change, and it will give you the different poles location on the S-plane, and it will also affect the time response analysis. For example, when we see the step response, we can see the step response change in its response depending on the location of the poles, which is contributed by the variation number of gains of the feedback system. And this is actually a technique that developed by Walter R. Evans. All right. Next one, the root locus technique can be used to analyze and design the effects of loop gain upon the system transient response and stability. Okay, so it's provide solutions for system of order higher than 2. So for system second order and first order, we have analyzed them in the previous lecture, and then we can use the formulas that we have developed or we have learned: TS, TP, TR, TD, tau, time delay. And then for the higher order than 2, which is third order, fourth order, fifth order, it is one of the possible technique that can be used, which is this root locus, to examine its transient response and its stability. And then what it means by the transient response, we can describe quantitatively the performance of a system as various parameters are changed. For example, when we change the value of gain, what we get is we get different value of percentage overshoot, different value of settling time, different value of peak time, and so on. All right. And then when we say about this stability, what we can see from the root locus is that it gives the graphical representation of system stability. We can see clearly the ranges of stability, range of instability, and the conditions that cause a system to break into the oscillations. Because when we plot the root locus, we plot it onto the S-plane. From the S-plane, I have explained to you in the previous lecture. When we have the S-plane, we can see where the poles located on the S-planes. So we can see when we identify those poles, we can see what are the response of the system, whether it is undamped, underdamped, critically damped, or overdamped, or unstable at all. Okay, so this root locus is very helpful in providing the graphical representation of the stability of the system. Okay, let's take example of a camera system. So in this case, we have the gain K varies. So the closed loop of the poles of the system varies. So we can see from this diagram here, and the B diagram, we have the subject position, which the input is R, and then the position of the camera is the output. And then we have the sensors, we have amplifiers, we have motor and camera. And say the amplifier give the system gain K1, and this motor and camera is designed and have the model and we can come up from the model the transfer function of the motor and the camera, which in this case is K2 over S plus 10. So when we find the equivalent or the closed loop transfer function of this motor and camera system, we can find the closed loop system is K over S square plus 10S plus K, where we have our K is simplified from K1 multiplied by K2. Alright, so this is our closed loop system. Closed loop system. And there is another term that is called loop transfer function. Loop transfer function or open loop transfer function is actually multiplication of C, G, and H. Okay? We have C, G, H, this is a compensator. We have the plant G, we have H, the feedback. So loop transfer function is actually C, G, H. Right? So in this case, our CGH equals to K1, K2 over S plus 10. Alright. Let me explain to you the examples using MATLAB. Okay. This is the example that I have shown to you in the slides. Okay, the slides. So where we have our K equals to K1, K2, and our closed loop transfer function is come from G over 1 plus GH. So in this case, what we have is actually we have K over S plus 10 plus K. Okay, S square plus 10S plus K. And the characteristic equation of the system is given by 1 plus GH. Okay, 1 plus GH equals to 0. So in this case, our characteristic equation is S square plus 10S plus K equals to 0. So what is the importance of these characteristic equations? Okay, so from this characteristic equation, we can find the closed loop poles. Okay, we can find the closed loop poles. So let's say our K is equals to 0. Now our poles is located at 0 and negative 10. And when we change the value of K equals to 1, the poles is changed as well. Okay, it changed to negative 0.101 and negative 9.899. So you can find the roots or the poles of these characteristic equation using this function. Roots 1, 10, 1. This is comes from the polynomial coefficients. We have S squared plus 10S plus K, so 1, 10, 1. So because this in this case K is equals to 1. So you cannot put K on the roots 1, 10K. The system cannot, the MATLAB cannot calculate. Okay, so you have to define the value of K. Alright, so when we see from these examples, you can see that when we change the value of K, in this case it is changed by 5 multiplication of 5, 0, 5, 10, 15, 20, 25, and until 50. So we can see the poles is changed from negative 10 to negative 9, negative 8, negative 8, negative 7, and negative 5. So you can see from this, so it's 10, negative 9, negative 8, negative 8, negative 7, and negative 5. So the corresponding value of gain is 0, 5, 10, 15, 20, and 25. So the same goes for the another pole. So we have pole at 0, negative 0, negative 1, negative 1, negative 2, negative 5. With the value of K from 0, 5, 10, 15, 20, and 25. So you can put it onto the S-plane where we have here 0, we have -0, -1, -2, -2, and -5 here. That corresponds to the value of k, 0, 5, 10, 15, 20, and 25. Okay, so what is root locus? The root locus is actually we replace all the poles that we plot onto the S-plane with a straight line or a line here, solid line, with arrows. You can see that when we change the value of k, it will move from this -10 to the right and from this 0 to the left. Okay, so I can show you the animation of this. So so let's see here. So it moved from -10 to right and from 0 to the left until it reached -5, and then it moved vertical directions, one to the up, one to the down. Okay, so this is, so I show you once again. Okay, so one to the, from -10 to the right, from 0 to the left until -5 here, and then one goes up and one goes down. Okay, when we want to make a root locus, we replace all these poles with a solid line. Okay, with solid line, and then we put arrow as we have seen just now. The movement of the poles is from -10 to -5, from 0 to -5, and then at this point it will break away from the real axis. One goes upwards, one goes downwards. So far, any questions? No questions? Alright, so this is the root locus. Alright, so this is the root locus that we want to learn in this chapter. So from this plot, what we can infer from this root locus, so we can see that the poles are real for gain less than 25. The poles are real, which is on the real axis, for gain less than 25. So this is K25, where we get poles is -5 and -5. Okay, so when we have gain that less than 25, we have 0, 5, 10, 15, 20, 23. The poles are real for gain less than 25, and the system response is over them. Why? Because the pole is located on the real axis and it has unique poles. Unique poles means two different poles. And at k equals to 25, we can see that the poles are real and multiple, where we have at this point, it is actually a critically damped system. Because this point we have two poles, multiple poles at the same location, which is -5 and -5. Then we know that the system response is critically damped and the value of zeta equals to 1. And then when we increase further the value of k, 25 and beyond, so in this case up to 50, so we have 25, 30, 35 until 50, the poles are complex conjugate. Complex conjugate means that in this case we have both values, it is a complex number for both values of real and imaginary axis. So in this case actually we have -5 plus minus j. -5 plus minus j. It can be j2, j3, j4, j5, and its complex conjugate is -2, -j3, -j4, -j5. And then we can see from this box, inside the box, a break box here, regardless of the value of k, the real parts of the complex poles are always the same. The real parts of the complex poles are always the same. So it's always -5 at this pole, at this root locus. And we know that from the equation, Ts equals to 4 over sigma d, which is equals to the value of this real axis. We know that the settling time for the system remain the same under all conditions of underdamped response. What does it mean? So we can see from the previous notes, when we have these poles on the vertical line here, we know that the settling time for this system will remain the same. Okay, the settling time will remain the same. What difference is that only the oscillation is different, because when we increase the poles upwards and downwards, where we have a different value of zeta, okay? and then we also have different value of omega n. That's why this oscillation is different, but the envelope is the same. The envelope is given by -5 in this case, and -5. So the rate of decays is the same. Okay. Any questions so far? No questions? Next. And as we increase the gain K, the damping ratio diminish and percentage of overshoot increases. And the damp frequency oscillation also increases, which resulted in a reduction of the peak time. So when we increase the value of K, okay, when we increase the value of K, what happened is, okay, when we increase the value of K, we can find the value of omega n, which is the distance from origin to the poles. So the omega n will increase. The distance from the origin to the poles is omega n. And then the zeta as well is decreasing, because we can see that this value on the real axis, it can be 1 and it can be greater than 1. And the value of zeta on the j omega axis is actually 0. So when we change the location of poles, the distance between the zeta to the j omega becomes nearer. So we can see that the value of zeta is actually decreasing. And we can actually find the value of zeta by cos theta of the hypotenuse here to the adjacent. So we can calculate that. And that's why we can see that when the damping ratio diminish, we will have a percentage of overshoot increases, because the zeta and the percentage overshoot is reciprocal to each other. Means it is berkadaran secara songsang. It is percentage overshoot equals to 1 over zeta. Okay. And the damp frequency of oscillation is the omega d, also increases, so which result in the reduction of the peak time. So we can see from this peak time, it depends on the value of omega d. So the larger the omega d, the TP will be smaller. Means it is require less time to reach peak time. Where at that point the percentage overshoot is maximum. Okay. And from the plot as well, we can see that the system will always stable. Why? Because regardless of the value of K, what we can see here is that the value of poles is always located on the left hand side of the S-plane. And we have learned in the stability chapter, when the when all poles is located on the left hand side of S-plane, the system is stable. Okay?